So let's see what we've seen so far. We've seen mistake-driven learning, and we've seen pack learning. These are two broad umbrellas to answer the same question: what does it mean to learn? With mistake-driven learning, we define learning by counting the number of mistakes and bounding them. And if the number of mistakes is bounded, we declare learning to be successful. With pack learnability, we have this whole definition that talks about with high probability, we'll get a classifier that makes low error. Under these frameworks, there are various learning algorithms. We've analyzed some learning algorithms, notably perceptron, under mistake-bound learning. We've looked at some algorithms that came out of pack learnability, AdaBoost and SVM, and such things. And in all cases, the one common thing that we had was we had the inputs where whatever they are, but the hypothesis functions take the input and produce a label, right? Hypothesis always takes an input and produces a label. Today and on Tuesday, we're going to be exploring a slightly different way to think about it, which falls under the name of Bayesian learning, which is another way to answer the question, ask the question, or approach the question: what does it mean to learn? Under this regime, there are many standard learning algorithms. Normally, I would spend time on naive Bayes and logistic regression, but this semester I'm not going to do naive Bayes because we don't have time. But the material is online and you can take a look at it. We'll be looking at logistic regression. Today, we'll look at what Bayesian learning is. I'll introduce these two criteria for Bayesian learning, namely maximum a posteriori criterion and the maximum likelihood criterion. I'll instantiate maximum likelihood for two instances. One of them involves a certain problem where a natural distribution is the binomial distribution. Another one involves a certain problem where the natural distribution is the normal distribution. I'm hoping we at least get till here today. And on Tuesday, we'll pick up from wherever we stopped today, and then we'll move to logistic regression, which comes back to the question of learning a classifier, a binary classifier, under this framework. So let's look at Bayesian learning. When people talk about probabilistic learning, there are two different notions that get conflated. One of them is that the concept you're learning is probabilistic. Namely, the function that you're learning is you're learning a function that takes some input x and produces a probability distribution over some output space. So your function produces a probability. So I have a function, I need to mimic a concept C, where C produces a number between 0 and 1 that you're going to interpret as a probability. And it turns out that the kind of learning theory that we've seen so far can be extended to this framework as well. There's another way to think about it, which is the key point of Bayesian learning, which is the use of probabilistic criteria to define the process of learning. What's the process of learning? The process of learning is selecting a hypothesis. So the hypothesis space itself can be deterministic. It could be Boolean functions. It could be linear classifiers. Or the hypothesis space could be probabilistic of its own. So this hypothesis could be a function that looks like this. That's orthogonal here. Bayesian learning is really a way to think about learning where the choice of hypotheses itself uses a probabilistic criteria. Let's kind of dive a little deeper into this. The goal of learning is to find the best hypothesis, given some data. You have a set of functions, capital H, you have some data, D, and the data is observed, of course. And the goal of learning is to find a hypothesis that best explains the data. In Bayesian learning, we'll define the word best as the most probable hypothesis. The best hypothesis is the one that is most probable given the data. But how do you actually compute the most probable hypothesis? That means you need to have some way to define a probability distribution over the hypothesis space. As among all the functions, for each function, you're asking the question, given the data, what's the probability that this particular function generated the data, or that other particular function generated the data, and you enumerate all possible functions and find the one for which this value is the highest. So we need to define a probability distribution over the data, which means we need to actually know a little bit, or we need to assume something about how the data and that's being observed is generated by the hypothesis. We will see later on that we can be quote unquote Bayesian about other aspects also, like the parameters. We can assume that the parameters themselves are coming out of a probability distribution. So you pick a model from some distribution, that model labels an example, and it gets a little complicated if you've not seen it before. So let's go one step at a time. But before we get into any details, the approach of Bayesian learning allows us, it naturally leads to practical learning algorithms. It gives us a framework, a sort of a mathematically sound framework for combining prior knowledge about a domain with observed data, so that it's not purely data driven. It's the hypothesis selection process is governed by data and any prior knowledge that you may have about the hypothesis itself. And we'll see some examples of this later on. It also gives us a conceptual framework to think about learning and analyzing the process of learning. We'll not spend too much time on these last 2 points. We'll be looking at the first 2 in this class. At the heart of everything lies something that you must be, lies an idea that hopefully you have seen before. You must be intimately familiar with. This is the Bayes theorem. People have seen the Bayes theorem, I hope. Have people seen the Bayes theorem? No? Okay, good. So the expression is rather simple. You have random variables x and y. The probability of the conditional probability of y given x is nothing but the conditional probability of x given y times probability of y divided by p of x. I will use this shorthand here. When I say probability of y given x, I really mean probability that the random variable y takes the value little y, given that the random variable x takes the value little x, equals blah, blah, blah. The bottom one is a mess to write, so I will never write it again. So let's go back to the Bayes theorem. Let's stare at this a little bit. We have this expression, this term, P of y. It's called the prior. So the thing that I care about is some probability distribution over the random variable y. And the 2 sides of this expression are they both involve some distribution over the variable y. On this side here, we have probability of y given x, and on this side here, we have probability of y given nothing. P of y is called the prior probability. It's essentially our belief in that random variable before having observed any data, any x. The middle term, P of x given y, is called the likelihood. If y were taking on a certain value, the likelihood term is asking, what's the probability that you observe this particular x that you are currently observing? So, for instance, y could be the statement, the sun rises in the east. And x could be, what's an effect of the sun rising in the east? Shadows if the sun rises in the east, the shadows would face westwards in the morning. So this expression here is asking, what's the probability that the sun rises in the east, given that you see that the shadows are westwards in the morning? I don't know why you can't see the sun, but let's not worry about such small details. The prior is asking, independent of anything to do with shadows, what's your belief that the sun rises in the east? This term is asking, given that if you believe that the sun rises in the east, what's the probability that the shadow would be westwards? That's the likelihood term. And P of y given x is called the posterior probability. Posterior as in after. The probability of y after having observed x. The power of the Bayes theorem is really that it shows you an expression that relates the posterior belief to the prior belief, mediated by this likelihood term. The posterior probability of a random variable conditioned on some observation is proportional to the prior probability times the likelihood of the observation given whatever you given the y. So posterior is proportional to likelihood times prior. This is something that we'll keep using all the time. Any questions about this? Hopefully you've seen this before, right? Everything that I said so far, including all the things about astronomy, should be familiar to you, about suns rising the east. So the other thing that hopefully that you've seen before, quickly summarizing everything that you need to know about probabilities in one slide. If you have two variables A and B, the joint probability of A and B is nothing but the conditional probability of A given B times the probability of B, which is also the same as conditional probability of B given A times P of A. It turns out that these two together give you the Bayes rule. The probability of A or B is nothing but probability of A and B minus joint probability. And we have the definition of independence. Two variables A and B are independent if their joint probability is nothing but the probability of the product of their individual probabilities. Equivalently, probability of A given B is nothing but probability of A. Or probability of B given A is nothing but probability of B. This stuff should be fairly straightforward. And then there's a little bit about total probability. If you have mutually exclusive events, A1 through AN, what that means is the sum of the probabilities of the A's adds up to 1. Then for any B, I can write it out as the probability of B is nothing but the probability of B given A times probability of A for each of those A's. So I can write for any variable probability of X is nothing but probability of X given, let's say, Y equals 1 times probability of Y equals 1 plus probability of X given Y equals 0. This statement, this is true if and only if the Y can take only 0 or 1. In other words, probability of Y equals 1 plus probability of Y equals 0 adds up to 1. And I can make the summation as long as I want for as many values of Y as there might be. This is just a quick refresher. I'm not expecting that anything here should be shocking to any of you. Let's go back to Bayesian learning. Our goal is we're given a data set, capital D, and we wish to find a hypothesis that is the best one given the data. And our definition of best for today is the data set, the hypothesis that's the best is the one that's the most probable. We're going to use the conditional probability of the hypothesis given the data as the object of study. Now let's stare at that a little bit more closely. Probability of the hypothesis. Do you have a question? Oh, no. The probability of a hypothesis given a data set. Given the data set, I want to find the hypothesis that has the highest probability. So if I can write down this expression, and I can frame the problem of learning as maximize over all the hypotheses, the probability of the hypothesis given the data. But this is actually a posterior distribution. It's asking what's the probability that among all the hypotheses that exist, this little h is the one that got chosen, that generated the data, having observed the data set capital D. The sort of clever insight that goes into this is the observation that we are treating H and D as events. H is a hypothesis, but really here, when I write it like this, H is the event that the hypothesis H is the true hypothesis. When I say capital D in the conditioned part, in the conditioning here, that's really an event that among all the possible data sets that could exist, the one that we have is the one that is the one that showed up. So H and D are, hypotheses and data sets, but they are also events. They are or random variables. We have an event that capital D that says this particular data set is the one that we observe. We have the event capital H that says little h. Sorry, we have the event little h that's saying that that's the hypothesis that generated the data. Or actually, no, not generated the data. That's the true concept. That's the little h is the event that says the function h is the true concept behind this phenomenon. And we are asking, this posterior probability is asking, what's the probability that you observe that little h is the true concept, given the fact that among all data sets that you could have observed, you see this thing? Questions about just this sort of a mental model here? Because after this, we're just going to be mechanical about this. From now on, we're just blindly going to observe the Bayes rule, and we will be done very quickly. So let's blindly apply the Bayes rule. And we have a conditional probability. We can use the Bayes rule. P of h given d is nothing but P of d given h times P of h divided by P of d. Now this we can apply the interpretation of the prior and the posterior on this expression here. P of h given d is the posterior probability. It's the probability of that h is the true concept, given that a data set d is observed. P of h by itself is the prior probability. Before observing any data, what's your belief that this particular hypothesis was the true concept? You could ask me, why would you have any belief? Not having any belief is also a certain probability. It's essentially assuming that all hypotheses are equally likely, so you have a uniform distribution. Maybe you know something about this. Maybe you have some expectation that your hypothesis H, let's say, for example, I'm just going to use an example that I won't elaborate on later, but let's say your hypothesis is a decision tree. Maybe you have a belief, before you see any data, that shorter trees are more likely to be generating the data. So you might construct a certain prior distribution that assigns a higher prior probability to smaller trees, so that you could invent a certain distribution that assigns a higher value of P of h to a tree whose depth is low. And you have to think about how you operationalize that, but you could encode that kind of a belief into your prior. This is what I meant when I said the Bayesian perspective allows you to encode background information about the problem. You do that by playing with the prior. The prior comes into play before you observe any data. And then there's this term, likelihood. The likelihood is asking, what's the probability that you observe this data set, D, if h was the true function? If h was the concept, what's the probability that the labels that you might have, for example, would have been assigned? And what Bayes rule tells us is that P of h given d posterior is proportional to the prior And the constant of proportion or the proportionality is basically the likelihood. There's also this extra term, the denominator here, which is simply independent of any information about the hypothesis, what's the probability that the data set D gets observed? Turns out we're not going to worry about that at all. Can someone guess why? Yeah. So the answer is it's constant over all hypotheses. P of D is a function that does not involve an H. And our goal is to maximize over all possible H, which means it's enough if we just maximize the numerator. So we'll never really care about P of D. We'll just drop it off and we'll just worry about the product of the likelihood and the prior. Any questions? Did you have a question? Yes.
I guess, does that just mean that we're assuming the probability that A to B is there's one?
Well, not really. We are not actually assuming that. We are just noting that that particular expression is a constant as far as the optimization with respect to H is concerned. Because it's a constant, we don't ever need to calculate it, so we might as well not, we can ignore it. Instead of P of D, imagine that I had the number 14 there. I could have had a number 14. And if I ask you to find the value of, find the H that maximizes the P of H given D, you could keep the 14 along, or you could drop it because it's a constant. Because the number 14 doesn't depend on H. Just like the number 14 doesn't depend on H, P of D doesn't depend on H. So it's, as far as that particular optimization is concerned, P of D is a constant. Okay, now that we have this sort of a mental model, let's look at the two criteria for learning in this framework. The two criteria are called maximum a posteriori estimation and maximum likelihood estimation. Our goal is to find the most probable hypothesis. And that's literally maximizing the posterior probability of the hypothesis given the data. And so that gives us the MAP criterion. MAP is short for maximum a posteriori. HMAP is simply the hypothesis H that maximizes the posterior probability of the data of the hypothesis given the data, which is equivalent to saying by Bayes' rule, it's maximizing that expression there that we just saw. But because of this discussion that we just had, where the denominator doesn't matter, we can just have argmax of the product of the likelihood times the prior. Because the posterior is nothing but it's proportional to the likelihood times the prior. So often when we talk about the MAP hypothesis, we don't even go through this process. We just write down a likelihood term, we write down a prior term, and we say we need to maximize the product of that. Question?
So all this is saying is we want the hypothesis that has the highest probability.
According to this, yes, that's right. That's literally what it is. We want the hypothesis that has the highest, well, I would change that slightly. We want the hypothesis that has the highest conditional probability given the data. So we have the maximum a posteriori criterion, which is this. But now the question that I mentioned earlier shows up. It's the product of the likelihood and the prior. And what if I don't have anything intelligent to say about the prior, about the hypothesis space upfront? I know nothing about the hypothesis space. All I know is something in this set of functions is the true hypothesis, is the concept. What if I know nothing? Knowing nothing about the hypothesis space is equivalent to saying that every possible hypothesis in that hypothesis space is equally likely. In other words, you're assuming that this thing is the uniform distribution. If you assume that the prior probability is uniform, that means this becomes another constant that goes out. So the only thing that matters is the likelihood. So then what we get is the likelihood, maximum likelihood criterion. The maximum likelihood criterion, which for some reason many years ago I decided to call HML. Not very fond of that name. You usually see MLE, maximum likelihood estimate. The maximum likelihood hypothesis is simply the hypothesis that maximizes the likelihood term. The maximum likelihood estimation assumes that the prior probability over the hypothesis space is uniform. Any questions about this? Have people seen this stuff before? I mean, if you've done the intro to data science, the foundations of data analysis, you may have seen maximum likelihood estimation. I don't know if you see it exactly the same way, but you may have seen it. Yes.
But it's another like distribution than not uniform distribution.
Then you are in this world here. Then you have to define that distribution, and you need to somehow bring it into a form that you can then give it to a maximizer.
Okay, we are assuming it's a uniform distribution.
In only here for maximum likelihood estimation. For maximum likelihood estimation, you assume that the prior over the hypothesis space is uniform. Yes.
Yes, is there any benefits to using one of these over the other?
Yes.
Or
There is. There's a very clear benefit in the following way. If you have domain knowledge about your hypothesis space, might as well use it, right? So this is almost like a borderline philosophical point. If you know something about the problem, then why do you not want to bias your learner towards respecting that knowledge? Chances are, if you have enough data, maximum likelihood estimate might find the same thing. But why not make the problem of learning easier by injecting knowledge through the prior? So that's the advantage that you get from, in general, the Bayesian perspective. I say that now, and when we come to logistic regression, you will see that we've been doing that in a different way all along, but we'll see that later. Oh, as a technical detail here, often rather than maximizing likelihoods, it's often easier to maximize log likelihoods. So you will see log likelihood as a phrase all the time. You don't maximize likelihood, you maximize log likelihood. You don't maximize the sum of the product of the likelihood and the prior. You maximize the sum of the log likelihood and the log prior. Operating in the log space tends to work more nicely for a lot of the optimizers that we have. Let's think about, all I have done here is tell you what the problem is. I've not told you about how the problem is actually solved. Let's think about how one might solve this problem of learning. You can, so I could have a brute force learner that enumerates every single hypothesis in your hypothesis space, because that's literally what that means. And then for each one of those, it calculates the value of the posterior probability P of h given d, and then it finds the one that has the highest value. It's a horrible algorithm because you have to enumerate every single hypothesis. If you're lucky, you might have a hypothesis space that's finite, right? If you're lucky, slightly less lucky, you might have a hypothesis space that is countable. Imagine that you're trying to apply this idea for a linear classifier. Enumerate every possible linear classifier, compute the probability of the data set given the hypothesis, or hypothesis given the data set, and then find the one that is the most probable. That's a terrible idea. If you want to keep someone very busy for an infinite amount of time, and they are gullible, you could ask them to do that. But conceptually, that's literally what this is doing. Conceptually, what we are doing is we are searching over the entire hypothesis space. For every single hypothesis, you are assigning this posterior function, computing the value of the posterior of that hypothesis, and then finding the one that's the maximizer. Conceptually. Actually, you don't do that. You actually either try to solve this problem analytically on paper, or you use an optimizer to solve this algorithmically. More often than not, it's algorithmic. But we look at one example where you can actually solve this on paper. Turns out this expression is difficult to compute for most, except the simplest hypothesis. And this maximization is difficult to do for anything that's reasonable. Let's look at a couple of instances. We have 15 minutes. Let's see if we can get through one, maybe even both of these in the 15 minutes. I'm going to show you two examples of maximum likelihood estimation. Maximum likelihood estimation involves finding a model, H, that maximizes the likelihood of the data given the hypothesis. To operationalize this for a new problem, you need to first define the hypothesis space. We need to do that for any machine learning application. We need to define what set of functions we are searching. Either explicitly or implicitly, we are doing that. And then we need a model that computes this probability, this likelihood term. Essentially, what it says is how is the data generated if the hypothesis were something. And we need to make an assumption about that expression there. Let's instantiate these two steps for two problems. Imagine that there's a company that makes light bulbs, and the CEO of that company comes to you and hires you for a consulting job, where your goal is to figure out how many light bulbs are faulty. And of course, you say yes, because that's what we do. And but you need to get some information about the problem. So you ask, the first question is, are they all identical? Meaning, is the process that produces the light bulbs all the same? And of course it is, because it's not like every light bulb is made by hand. It's some factory that's doing it. Because they are all identical, you can actually conduct an experiment. Can someone guess what the experiment is? Yes.
Just sample some light bulbs and see how often they.
Yeah, exactly. So let's say you try out some light bulbs. You try out 100 of them, and 80 of them work and 20 of them don't. That means your probability of failure is 20%. Doesn't seem particularly shocking, right? How do you know it's 20%? Yeah.
Is it because our sample is supposed to be indicative of our larger set?
Okay. That's one part of the answer, yes. But why do you get 0.2? Why not 0.3? Why not 0.21? How did that number come into existence?
20 divided by 100.
That's correct. But why is that the right thing to do? Maybe I should have done 40 divided by 100. Or maybe I should have done 80 divided by 20. Or that doesn't even make sense. Maybe I should do 20 divided by 80. If I know that I need a number between 0 and 1, using these three numbers, I can do many different things that gives me a number between 0 and 1. Maybe I can get 20 divided by 80. Yes.
Maybe because for that particular sample only 20 bulbs that was taken.
Yes. How do you know that to compute the probability, you divide 20 divided by 100? Why is that the right operation? Now I'm asking this question and you're looking at me like, well, it's obvious. I mean, But actually, it turns out that you can prove that this is the right answer. And let's do that using maximum likelihood estimation. Have people seen this before? Okay, good. You have. Okay, one person's seen this before. Then don't share the answer yet. So let's say that the probability of failure is P, which means the probability of success is, of course, 1 minus P. And each trial is IID. Remember, I asked if all the light bulbs are identical? This is what I meant. The success or failure of each light bulb is independent of the success or failure of other light bulbs. Well, of course, that's not true in real life because the light bulbs are produced. Let's not worry about that. So each trial is IID. So we can, let's say you have a data set D that has 80 light bulbs that work and 20 light bulbs that do not work. So the probability that you observe this particular data, given the hypothesis that the probability of failure is P, is nothing but the probability that a particular light bulb fails is P, 20 of them failed, and they're all independent, so the probability of seeing 20 failures is P power 20. The probability that one of them randomly succeeds is 1 minus P. 80 of them succeeded, so it is 1 minus P power 80. And then you can shuffle these in many different ways. The number of ways in which you can shuffle them is 100 choose 80. So the probability of seeing this particular data set, here I call it a data set, it's a very generous term, it's just literally those two numbers. The probability of seeing this particular observation given a model, a hypothesis that your probability of failure is P, is this expression there. Now I can apply maximum likelihood estimation. Essentially, I am asking, given this likelihood term, likelihood is nothing but probability of the data given the hypothesis, given that expression for the likelihood, what's the value of P that maximizes this quantity? So this is actually rather simple to work out. So let's work this out. Probability of data given the hypothesis is 100 choose 80, P power 20. I want to maximize that expression. And one of the first things that one might do to solve this maximization problem is not to actually work with this directly, but work with the log likelihood. So let's take the log of this. So the log likelihood of data given the hypothesis is 20 log P plus 80 log 1 minus P plus some constants. Basically log of that 100 choose 80. I want to maximize that expression. How do I maximize this thing? Shouldn't be too hard. This is a calculus question. I want to find the maximum of 20 log P plus 80 log 1 minus P. I can take the derivative with respect to P. So the derivative of the log likelihood is what? Help me do this because I know I'll make mistakes while writing. 20 over P minus 80 1 minus P, and I set this to 0. Okay, so that means 20 over P should be equal to 80 divided by 1 minus P. Let's solve this quickly. So 20 minus 20P equals 80P. What I have here is a proof that the right thing to do is to divide 20 by 100. Why? It seemed like an intuitive thing to do, but what was amazing is that when you were doing that in your head, what you were actually doing is solving this calculus problem. Right? That's how you did it. Often maximum likelihood estimation gives you these sorts of intuitive answers. So the probability of the maximum likelihood, when you actually do, when you report that the probability of failure is 0.2, you're implicitly assuming a lot of things. You're assuming that the light bulbs are generated by this process that's IID. You are assuming that there are Bernoulli trials here. Each light bulb has a probability of being successful or failing independent of everything else. And there are no, it's not like you're taking measurements about the shape of the light bulb and all that. It has an independent probability of being successful or not. And it's completely, the entire model is a single number, P. And you're searching over the space of all possible models, basically all values that P can take. And the right tool for the search is calculus, because you're taking the derivative of the log likelihood. Oh, that's another thing that you do. You don't work with likelihoods, you work with log likelihoods. And this also brings up another question here. What about the prior? Well, I have no idea what values of P are better or worse. So I'm not making any prior assumptions about the hypothesis space. So essentially, I'm not operating in maximum a posteriori. I'm operating in the maximum likelihood case. I'm assuming a uniform prior here. And all values of P are equally likely. And it's purely dictated by data. And then you're applying this process. What, the rest of it is just mechanical. Take the derivative and set it to 0. Any questions? So what you've done here is a rather sophisticated amount of math, right? I mean, it's the kind of math that you might see in early college or late high school, but the math is not trivial, but still the result is something that is fairly obvious. You can generalize this to, instead of 20 and 80, you can have A that don't work and B that work. The best probability, according to the log likelihood, the maximum likelihood criterion, is the one that maximizes the likelihood. Or equivalently, the one that maximizes the log likelihood, because log is an increasing function. And you can just apply, go through the same process. I've done this symbolically here rather than with the numbers 80 and 100. And you can take the derivative, set it to 0, and you'll get something that's A divided by A plus B, assuming that A is 20 and B is 80, you get 0.2. This is a learning algorithm. I didn't do any learning. I didn't have an algorithm here. I just did it on paper. The model that we assumed here was the Bernoulli. You could have assumed a different model. That means you'd have obtained other solutions here. You could have assumed a prior over the value P, and there's a whole literature on what's the right kind of prior to use for Bernoulli. You could assume, for example, that the value P itself is a random variable that's sampled from a distribution called the beta distribution. That means your maximum likelihood estimation no longer works. You have maximum a posteriori distribution. And you can solve that also on paper. Any questions about this? Two people not know. And you think, maybe you're thinking this is too simple. You're taking 20 light bulbs, and this is not why you came to machine learning. Let's actually make this a little bit more complicated. Let's look at another distribution, another problem that involves a normal distribution. In all problems, you need to first define the hypothesis space, and you need to have some model that says how is the data generated if your hypothesis was some h. The problem that we have here is the following. Your hypothesis consists of real valued functions. Functions that take an input x, which is a d-dimensional vector, a feature vector with d features, and produces some real number y. In other words, you have a regression problem. The hypothesis space consists of a collection of real valued functions. Now, suppose you assume that the training data is generated in the following way. Some input xi is sampled from some fixed unknown distribution. We don't care right now. And there's a true concept f, a true function that is applied to this to get the label f of x. But before nature gives the label to you, an adversary comes in and adds a little bit of noise. That noise is, I'm calling it, for the ith example, the noise is EI. This noise is drawn by the adversary from some Gaussian distribution, and the adversary doesn't tell you what the parameters of that Gaussian are. It can do that, right? So this is how you construct your data set. So the label that you observe yi is not just the f applied to x, but it's f of x plus some random noise. There's no random noise in the labeling part. All the randomness is here. And then you collect a data set that consists of many, many examples of this kind, m examples of xi and yi. Xi is a feature vector, and yi is a label which all you know is it's not the correct label. It's close to the correct label because of this process that happened before you got the label. Okay, is the setup clear? And you have a data set that was created this way. Now let's say that you have a certain hypothesis, H, and you want to know what's the probability that H was the thing that generated the data. If H were the true hypothesis, the error on that example is the difference between Y and H, right? H of X is the prediction, and Y minus H is the error. Now, if H were the true hypothesis, that error would be Gaussian. If H was equal to F, then that error would be Gaussian because that's exactly how the data was generated. So you could try to you can assume that that error comes from a Gaussian with zero mean and some standard deviation, sigma, that you don't have access to. You can compute the probability, and I'm kind of playing a little loose with the probability density and probability mass. Let's not worry about that. The probability that yi is observed if h was the true hypothesis, the true function, and for this particular example, is simply the normal distribution, is based on the normal distribution. Again, there's a little bit more here that I'm playing loose with. That expression should be familiar to you. That's the normal distribution. So this is the probability of seeing one data point. Each example is produced independently of everything else. So the probability of seeing the data set is simply proportional to the probabilities of seeing all the product of all these probabilities, because every example is produced independently by your adversary. And you can take my word for this. You can put all of this together and, oh, you don't have to take my word for this. You know what? Let's stop now. I'll stop here because we are at time, and I'm definitely not going to get to the end of this by today. On Tuesday next week, we'll pick up from here, and there's an interesting thing that comes at the end of this process. What you'll come to at the end of this is something that we've seen before, and something you've seen before even before we started this semester. Just like with the coin toss thing, right? You came up, maximum likelihood gave us an answer that you could have guessed without actually doing any of that. Here, maximum likelihood will give you an answer that you have already guessed before without going through this process, except this is sort of a justification from the Bayesian perspective. With that, I will stop. We'll pick up from here on Tuesday. Don't forget your homework and all those other deadlines. I have office hours at 2 o'clock. If you're interested, you want to talk about things, we can talk about that.